Hi everyone, welcome to our senior design project on quantum computing and encryption. Um, this year I had the opportunity to work with an amazing team as well as some amazing sponsors, and I'm really excited to share what we worked on this year with you guys. So introducing the team, we had, like I said, an amazing team of 5 members. We had Francis, Ryan, Phil, Najaj, and myself, and together we worked on solving um, some creating some programs in classical computing and as well as quantum computing, and comparing the runtimes to see what is the true potential of quantum computing. Um, our first semester, we worked mainly on doing research on both the classical and the quantum side of things, as well as building a bunch of classical encryption algorithms that allowed us uh, to see how encryption is working on the internet today. One of the first things we built was a pseudo-random permutation generator, which we built in both Python and in C, which allowed us to create randomness that was essential for implementing our one-time pad, which we also built in C. And our one-time pad allowed us to encrypt bits and transmit them over the internet to each other, um, so that an eavesdropper would not be able to interpret what we were saying, because while they were in transit, the bits were encrypted. Um, this also led to us building a video encryption algorithm with the help of our sponsor, Steve. And our video encryption algorithm was able to take a video from one end and send it over the internet to an end user, and the end user was able to decrypt it and view the video clearly. But while the video was in transit, it was encrypted into unrecognizable snow and did not transmit any of the information uh, of the video while it was being transported over the internet. Um, as well, after building all of these things, we also did some extensive research on quantum computing in general and its potential in the field. What exactly allows quantum computing to offer so much potential over classical computing? And I'll share some of the findings with you on the next slide. All the code that we've worked on is available on our GitHub, and that will be linked at the end of our presentation if anyone's interested in looking at what we were able to build this semester. Second semester, we got some hands-on experience with IBM Quantum. IBM Quantum has an amazing platform where you can actually build your own quantum circuits and run them in real time and get back some results. And so this was essential for us getting a good understanding of how quantum computers are running and what exactly is giving them the potential to run so much faster than classical computers at certain problems. Two really important principles in quantum computing come from quantum physics, and those two principles are superposition and entanglement. Superposition is the idea that when you have a quantum particle, its state is able to be multiple states at the same time. So comparing that to a traditional bit has to be either a 1 or a 0, and a quantum bit or a qubit has the ability to be a 1, a 0, or anything between 1 and 0, and it can represent all of these states all at the same time. So if you're trying to test a system that has a lot of output states, if you're able to incorporate quantum computing, you can test all of the output states at the same time with one run of the system. Whereas in classical computing, you would have to test each individual input to get each output. So quantum computing has the potential to drastically cut down computation time in certain problems. The other core principle is called entanglement. Entanglement is the idea that you can link one quantum particle to another quantum particle, and then the state of the first quantum particle can tell you the state of the second quantum particle, and vice versa. This allows you to link quantum particles together and then determine the state of the entire system by just checking one of the qubits instead of having to check each individual qubit. And so this also helps with computation time when building with quantum circuits. In order to actually work with IBM Quantum and build quantum circuits, we had to learn the Qiskit framework, which I have an example of on the next slide. And it's essentially just a library you can import into Python that allows you to build quantum circuits and communicate with IBM's quantum computers. One of the most talked about quantum algorithms that is out there right now is called Shor's algorithm. Shor's algorithm is a quantum algorithm for solving the factoring problem, which is a very essential problem in today's encryption. A lot of heavily used encryption algorithms rely on the factoring of a large number in order to keep all the information safe. And Shor's algorithm is able to solve this problem a lot faster than a traditional computer. We're comparing Shor's algorithm and its runtime to a traditional a classical computing factoring algorithm known as Siva-Vikin. It's one of the best factoring algorithms in classical computing, and Shor's algorithm has the potential to drastically outperform it. And we'll talk about that in the future slides. The last thing that we really looked at is the potential of quantum computing in the future. Right now, it's far too expensive to maintain and create quantum computers for the average user to have access to them. But as we saw with classical computing, originally classical computers were very expensive and hard to maintain. And so the average person wasn't able to have their own. But there was an explosion of computing power that came in after a couple of decades of research went into the field. And so we expect a similar thing to happen in quantum computing, where we reach a certain breakpoint where quantum computing becomes readily accessible to people very quickly. So trying to determine when that breakpoint is something that we were concerned with in our project. So this is an example of a quantum circuit that we were able to build in Qiskit. And this is actually a quantum circuit that will run Shor's algorithm, which will factor the number 15 and return to you the factors of 15 after just one test. A few things to note. On the left side, we have 5 H gates, which all represent our 5 quantum bits. And each one of these bits are able to represent whatever state they want at the same time. So you are able to test the numbers 1 through 16 to see if any of those numbers are a factor of 15 all at the same time, and then output the results in one test without having to run multiple tests to check for all the factors of the number 15. The other important thing to note is we have our classical bit, x, which is actually entangled with all of our quantum bits. And what this allows us to do is we can actually read the output of our quantum bits without actually checking the quantum bit, which is very important for keeping the machine running properly. Because if you actually check the state of a quantum bit, you force it to collapse to a single state instead of being all possible states at the same time. So by entangling it with a classical bit, we can actually read the result of our quantum bit without forcing it to collapse. And so moving on to talk about the actual time complexity advantage of quantum computing, the theoretical limit in classical computing to factor a large unknown n value would be actually exponential. The exact formula is 2 raised to the power of n to the 1/3 times log base 2 n to the 2/3. And as I said, this formula is actually exponential. So as n increases in size, the amount of time it takes to find the factors of n will increase exponentially. In the case of quantum computing, the theoretical limit for finding factors using Shor's algorithm is actually log base 2 to the n. And so this is a logarithmic increase, a logarithmic scaling as opposed to exponential scaling. So as n gets very large, the quantum computing potential does not, the time complexity of quantum computing does not grow nearly as fast as classical, which means that quantum computing should heavily outperform classical when it comes to trying to find the factors of extremely large n values. So an important thing to note is that the realistic limit with today's technology is actually log base 2 to the n to the 2.5. We aren't able to fully replicate the full potential of log base 2 to the n right now, but there have been test cases that have been showing that we can run about the speed of log base 2 n to the 2.5. And ideally, we will be able to get this time down to the theoretical limit within the next few decades. The last thing that's important to note is the base runtimes for the number 15. We can run the number 15, we can factor on both a classical and quantum computer. And as you can see, if we do this, the classical computer still runs about 33 times faster than a quantum computer at a small scale. And that has to do with the infrastructure for classical computing has been around for a lot longer than quantum computing. So there are ways to just increase the speed that don't yet exist in quantum. But ideally, we'd want the runtimes to be about the same once we get more infrastructure and more research into quantum computing. The next thing to talk about is the big O time complexity comparison between quantum and classical. If we assume that we've reached this level where we have a constant runtime and quantum and classical are able to factor the number 15 at about the same speed, then you can see the scaling really starts to come in. The classical line, the red line, you can see as the bits of n increase, the runtime time complexity begins to increase exponentially, whereas the quantum runtime is increasing logarithmically. So as n continues to increase, the runtime between classical and quantum will heavily favor the quantum computer. And the breakpoint that we were able to calculate here was when n reaches about 140 bits, then quantum factoring begins to outperform classical, which is a really interesting breakpoint to look at. So that breakpoint kind of leads to the question, when will quantum computers contain thousands of bits? And right now, actually, IBM last year released the Eagle model of quantum computers. And this model actually contains 127 qubits. So already we're getting very, very close to this, this limit where quantum computing will be able to outperform classical computing. The part that's not there yet is this Eagle model is still incredibly expensive to maintain and to build. So we're nowhere near it being accessible to the average user, the average computer user. But it's something that we're looking for in the future. What this quantum computer was able to prove, the 127-bit qubit Eagle model, was this idea of quantum supremacy. This photo was taken from NVIDIA Quantum Research. And NVIDIA was trying to predict this idea of quantum supremacy, which essentially means when a quantum computer will be able to outperform a traditional computer at certain select tasks. And they were predicting that around 10 to the second qubits, so around 100 qubits, would be the point where quantum computers will start to outperform classical computers at some select tasks. This idea of quantum supremacy is still being debated. People have argued that if you design a problem specific for quantum computers, the quantum computers can run faster than classical. But these same classical computers can actually solve the problem faster if you design the problem in a way that's better for them to solve. So it's still being debated whether or not we've really hit this quantum supremacy breakpoint. But if we haven't hit it yet, we'll definitely be close to hitting it in the future as we get quantum computers with more and more qubits. So in conclusion, we were just recently able to hit a breakpoint of quantum supremacy, even though it's still being debated. There are certain specific tests that have been shown where quantum computers are already outperforming classical computers at certain tasks. And so we only expect this to increase and for quantum computers to be able to outperform classical computers more consistently as time moves on. One of the caveats still is quantum computers are still far too expensive to maintain and to build for the average user. So most people would have to rely on a large company like IBM to provide access to quantum computers. And we're nowhere near the point where everyone's going to have access to a quantum computer in their pocket, or where it would be profitable to use quantum computers to break traditional encryption. But it's definitely something that we have to be wary of. Like we saw in classical computing, we hit a breakpoint where classical computers saw explosive exponential growth in in the amount of bits they had inside and the amount of in the speed they were able to process information. And so it's reasonable to assume that quantum computing will also hit a similar breakpoint like this, where the increase in computing power and speed will start to heavily increase. And this is when we might want to start being more concerned about if it's becoming too accessible to the average user, and if we need to rethink our encryption algorithms in order to protect the safety of everyone online. So finally, we have our sources page. We have a lot more sources available on our Google Drive. These are just a select few sources that were most relevant to our to this PowerPoint. We also have the link to our GitHub, where we have posted examples of everything that we have built for this project. So definitely feel free to check out the GitHub and download some of our code and run it yourself so you can see the same results that we were able to see. Thank you everyone so much for coming to the presentation. I hope you learned a lot about quantum computing, and keep it in mind